Let's talk about geometry and representations of geometric primitives today. So the plan is to give you an introduction to some of the basics of geometry as we are going to use it in computer graphics. So this involves the discussion of coordinate-free operations, particularly for geometric objects, the various basic elements, and then talking about primitives, talking about affine spaces, and finally the various representations that we're going to use for the geometric primitives that we're going to use to display our objects. So the reading for this comes from Angel again, chapter 3. The basics of geometry are from the appendices in the book by Angel. So let's begin. In our undergraduate and maybe even your high school, geometry is often introduced in a using specific coordinates, right? So we have learned geometry in the sense of Cartesian coordinates. So points are often specified as locations with 3 coordinates. We derive various results by algebraic manipulation of these coordinates. So for example, we compute area by manipulating these coordinates and so on, right? So this is a non-physical approach. I don't mean nonsensical, it's just non-physical approach. So in contrast, what we want to do in this class is to think about a physical approach. Points do exist whether you give it a coordinate system or not, right? Whether you represent them using coordinates or not, points do exist. So that's what we mean by a physical approach. So we would like our geometric elements to be independent of the coordinate system, right? So you have been introduced to this also, right? Very simple example is, for example, in Euclidean geometry, we talk about congruency between triangles or lines. So this property does not require coordinates. When you talk about congruent triangles, you talk only about, for example, the internal angles or the sides of the different, the lengths of the different sides and so on. Right? So this is the approach that we are going to take in order to introduce our geometric primitives. And we'll see that there are various benefits of this approach. Let's first talk about basic elements like scalars, vectors, and points. And then we will talk about how we will build more sophisticated geometric objects from these building blocks or these basic elements. Let's talk about scalars first. So we have let's talk about some examples, right? So the real line is an example of a scalar, right? So let's take 2 real values, alpha and beta, right? And let's talk about the addition operator. So we know that alpha plus beta is also a real. So we know that the reals is closed under addition. This addition operator also satisfies some nice properties. For example, the 0 element is well defined under addition. We know that the inverse of alpha, the additive inverse of alpha, is minus alpha, right? We also know that the addition satisfies nice properties such as associativity and commutativity. Right. So even though the scalars together with addition satisfies these nice properties, this does not help us as such represent our geometry. In order to move towards geometry, we need something more, right? So let's look at vectors. So an example for vector is something like velocity or force, right? let's talk about a couple of vectors u and v, and again talk about an addition operator between vectors. So we know again that u plus v is well defined if u and v are also velocities. Again, if you look at the collection of vectors u together with this addition operator, if the identity is well defined, the additive inverse is well defined, we have associativity, right, and commutativity, then we know that we have a vector space, right? Now in the case of vectors, we know that they have a direction and they have a magnitude. So there seems to be some idea of geometry that you can retrieve from a vector. However, the vector has no fixed location in space. So in that sense, it does not capture geometry to the full extent that we want it to, right? So in order to go there, what we need is a point, right? So far we have talked about scalar, vector, and now we want to talk about points. So with a point P, what we get is a little bit more. We have a fixed location in space. Now we can also talk about the addition operator. However, we want to first talk about addition of P together with a vector V. This makes more sense in our current context. So a point P together with a vector V gives us another point Q, right? Where this vector is V. So this naturally means that there is a operator such as this Q minus P that is defined. Now in addition to this, we of course have simple operators between these vectors. So you have alpha sub v, scalar multiplication is well defined, and of course if there are other vectors u and v, they can be added as before. So a point together with a collection of vectors seems to help us represent our geometry, and this is what we will take up in the next few slides. The first construct, or maybe the only construct that we'll talk about, where we have a point and a vector, is called an affine space. An affine space is essentially a vector space together with a single point. You can think of this point as the origin. The vector space is a collection of vectors, and you add a fixed point, the origin. So together this gives you an affine space. Now in this affine space, we can talk about various operations that we talked about. Vector addition, scalar vector multiplication, point and a vector addition, scalar operations, right? Scalar multiplication, scalar addition, and so on. Let's think about some interesting geometric primitives which can be represented as affine spaces, right? Let's talk about general geometric elements first. A line is an affine space. It's a very special affine space that is defined in this following way, right? So a point P sub 0 together with plus alpha times D, right? So this is the affine space that gives you a line. So all points on this line are defined by a single parameter alpha that tells you how far you are from P sub 0 in the direction D. Of course, alpha can take positive and negative values. So there are many ways to think about this. You can think about the line as all the points that you can reach by walking from P sub 0 in the direction of the vector D. Now, of course, in your high school, you have looked at various kinds of representations of lines. So these various representations of lines are already well known, so I won't talk about them much. I'll just list them here. The parametric form, which is robust and quite general. It extends to curves and surfaces, right? This is the parameter where you have a single parameter that helps you represent the line. Then there are the 2D forms where you explicitly write the equation between the y coordinate and the x coordinate. The implicit form where you have 3 coefficients, and of course the parametric form but in 2D, so where you specify the x coordinate and the y coordinate using a single parameter alpha. You may or may not have used all these representations. For this particular course, we are going to go back to the form that I introduced earlier. That's namely that using an affine space, so a single point together with a vector, right? Now this extends quickly to a representation of a line segment where you have the endpoints Q and R, right? So if you have the 2 points Q and R, they define a vector V, right? So naturally you can talk about any point on the line that connects Q and R in this following way, right? So you have P of alpha equal to Q plus alpha V, and of course V can be rewritten as R minus Q. So you have P of alpha equal to alpha R, it's R is a point, plus 1 minus alpha times capital Q, right? This is just an alternate expression, but I want to introduce this in order to talk about a generalization of this to planes and so on, right? So here if you notice, P of alpha is written as a linear combination of 2 points, right? So this is called an affine sum, right? And this is what we're going to talk about next. So let's look at affine sums. Consider P, right? We call P as an affine sum of P sub i's, where the coefficients alpha I are such that they sum up to 1, right? So this affine sum is what we're going to use to define our primitives and planes and so on, right? So more specifically, if we call we define this affine hull, right? So point P lies in the affine hull of P sub i's if P can be written as an affine sum of the P sub i's. If in addition your alpha sub i's are non-negative, then what you have is the convex hull of the P sub i's, right? So P is said to lie within the convex hull of P sub i's if it can be written as an affine sum where the alpha i's are greater than or equal to 0. So this term convex hull comes from the notion of convexity, right? So we have 2 objects here. It's clear that the object on the left is convex and the one on the right is not convex. So the way we define convexity is as follows. The object on the left is convex because if you take any pair of points PQ, the convex hull of PQ lies completely within the object. We can extend this notion of convex hull to a collection of points. So if you are given a collection of points P sub i's, the convex hull of P sub I is simply the collection of all points that can be written as summation of alpha sub I P sub I, where alpha sub I is greater than or equal to 0. Geometrically, this is the smallest convex object that contains the P sub i's, and it can be formed by imagining some kind of a rubber band that can be shrink wrapped to contain all the points. Let's talk about planes, right? We know that a plane can be defined using a point and two vectors, right? So any point on the plane can be written as P of alpha beta, which is equal to the point R plus alpha times U plus beta times P. Of course, we can rewrite this as the affine sum of 3 points P, Q and R. And the parameters again are alpha and beta. If we restrict alpha and beta, then we get a triangle rather than the entire plane. Right? So again, there are different ways to describe this. One way is as follows. So if you consider a triangle PQR, the way that we can describe any point T which lies within this particular triangle is by thinking of T as a convex sum, right? So before we get to T, let's look at S, which is a point on the line joining PQ. S is a convex sum of P and Q that is given by a parameter alpha. T is a point on the line joining S of alpha and R, and it is defined by a second parameter beta. So given two parameters alpha and beta, which lie between 0 and 1, we can define any point that lies inside the triangle PQR. Right? So what we have done so far is to use convex sums to define triangles. So the same way, of course, convex sums can be used to define line segments. Just to finish this discussion, we can talk about normals, right? So every plane has a normal, let's call it N. So we know that the plane can be defined by a point that lies on the plane and two vectors U and V that lie on the plane. The normal N is simply defined as the cross product of U and V, right? You may want to go and refresh how you want to write the equation of this plane in terms of either N and P or U, V and P. Right. Let's now talk about how we can represent the geometric objects so that we can do computation on them. So in order to talk about representations, I'm going to assume that you know about the basis of a vector space and its dimension. I will introduce coordinate systems for representing vector spaces. Then I will talk about coordinate frames that help represent affine spaces. We will talk about how to change basis of the frames and the coordinate systems. And finally, I'll talk about homogeneous coordinates that helps us to unify the representation of vectors and points. So in order to answer questions such as where is a point, we need a frame of reference. This helps us relate points and objects to the physical world. There are two examples of reference systems that we will use in computer graphics. One is the world coordinate system, which is essentially where our objects live in the real world. The second is the camera coordinates frame of reference. This is the reference with respect to the camera or the viewer. Let's first talk about coordinate systems. Let's consider a vector space and let's v sub I be its basis. Consider a vector v, which is written as a linear sum, summation alpha sub I v sub I. We call the alpha sub i's as the representation of v with respect to this basis v sub I. And the way we write this down is the usual form as a column vector of alpha sub i's. The basis is implicitly understood. So let's go through a quick thought exercise. Which of these two representations is correct? When you think about a vector v, in our mind, we may think that the image on the left is correct. However, the basis has no real position in space. So both are correct. The reason both are correct is that vectors have no fixed location. This is of course not useful for us in computer graphics. So in order to address this, we need frames. The coordinate system is no longer enough for us to represent our objects, particularly points. So we need to add a single point. So you've seen how to do this before. We do this by adding the origin. And after adding the origin, let's call it p sub 0, to a basis v sub 1, v sub 2 and v sub 3, we get a frame. This is called a coordinate frame. So let's now talk about representing points and vectors in a frame. So within a frame that is defined by this p sub 0, the origin, and v sub i's, a vector can, as usual, be written as summation alpha sub I v sub I. So we are restricting ourselves now to the 3D space. Each point in this space can be written as p equal to p sub 0, the origin, plus summation of beta sub I v sub I. Now let's think about how we represent points and vectors. Recall that we wrote p and v in this following form. I've generalized this now to points and vectors in n-dimensional space. So in 3D, for example, the representation of a point is beta 1, beta 2, beta 3. Of course, this is the column vector. I've written it here as a row. You can imagine that it's the convention is typically the column representation. V, a vector, is represented as alpha 1, alpha 2, alpha 3, where the alpha i's and beta i's are scalars. So if you think about this, the point P and the vector V have similar representations. There seems to be no real difference between the two. So this is confusing, particularly because a vector has no position. So we do want to distinguish between the two. The vector can actually be placed anywhere, right? So on the other hand, the point is fixed. So we do need a representation that is able to distinguish between points and vectors. The solution is to unify these two representations. And in order to unify, we need to introduce some definitions. In particular, two definitions: scalar multiplication with 0. So we define 0 times p as 0, the point 0, and 1 dot p as p itself. So now a vector and a point can be represented as the following. V, a vector, can be written by appending a 0 to its representation. So alpha 1, alpha 2, alpha 3 and a 0. A point P can be written by appending a 1 to its representation. So this new representation is called the homogeneous coordinate representation. In this case, it's a 4D homogeneous coordinate representation. Right? And again, the convention is to write down these representations as vectors, column vectors. Let's now talk about homogeneous coordinates a little bit more. So for a 3D point x, y, z, the homogeneous coordinate is x prime, y prime, z prime and w, of course, where w is 0 or 1. This actually represents the point wx, wy, wz and w. If we think of this as a point P, then the xyz coordinates can be obtained by dividing with w, right, in case w is not equal to 1. So in this way, we have a generic representation for a point using 4 coordinates. Of course, if w equal to 0, then what we have is a vector, and the first 3 coordinates tell us what that vector is. So what is the role of homogeneous coordinates in computer graphics? It's very crucial in 3 respects. This is the underlying representation for all points and vectors throughout computer graphics. All standard transformations for transforming points and other geometric primitives are implemented as simple matrix multiplications using 4x4 matrices, thanks to the use of homogeneous coordinates. So when I say transformations, I mean rotation, translation and scaling. We will talk about that more in the next class. Most crucial is that the use of homogeneous coordinates implies that the entire graphics pipeline is now able to work with a single unified 4D representation, right? And the architecture can now be optimized to deal with this specific representation. So you don't have to deal with 2 different representations for points and vectors, right? So now henceforth we will talk about points and vectors in this unified form. So let's now talk about different coordinate systems and how we can go from one to the other. This is more a revision of your basic linear algebra that you have done in your undergraduate days. So let's think about 2 representations of the same vector with respect to 2 different bases, right? So A and B are the 2 representations of this vector. So what this means is, if W is the vector, then W can be written as alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 using the basis V1, V2, V3. It can also be written as beta 1 U1, beta 2 U2 plus beta 3 U3 using the basis U1, U2, U3. Now, if I were to think about representing the second basis in terms of the first, right? So by second basis, I mean the u sub i's. In terms of the first basis, v sub i's. So let's assume that the three equations here tell us how to represent ui in terms of the v sub i's. Right? We know this is possible because v sub i's are a basis. Let's put down these coefficients that we have for the u sub i's in the form of a matrix. So M actually gives us the various coefficients gamma sub ij. So if M is this matrix, then using simple matrix manipulations, you can figure this out, that the representation A can be written as M transpose B, right? So this allows us to go from one representation to another, right? So if we have a point or a vector which is represented using, so in this case a vector, if it's represented using the basis v sub i's, then we can now represent it using the basis u sub i's in this way, right? So all we need is the matrix that transforms one basis into the other. So this analysis works exactly the same way for change of frames. So now let's assume that you have two frames, P sub 0 and origin together with V sub i's, and Q sub 0 another origin together with U sub i's. So a point or a vector can now again be represented in either frame, right? So let's assume that you can represent Q sub 0 and U sub 1, U sub 2, U sub 3 in terms of the first basis. So just repeating what we did earlier for coordinate systems, let's write down this expression in the form of a matrix. So the U sub i's can be written in terms of the basis V sub i's. Of course, Q sub 0 is a point. It can be written as P sub 0 together with a linear combination of the basis vectors V sub I. So this can be written in the more compactly in the form of a matrix. So all I'm doing here is just pulling together all these coefficients in the form of a matrix. So what this really means is that we are just saying M can be used to represent this vector, right, as M times the vector that is formed with the V sub i's, right? So V sub 1, V sub 2, V sub 3, and the point P sub 0. So given this matrix M, we can write the representation A in terms of the representation B as follows: A equal to M transpose B. The matrix M helps us transform one representation into another. So this is typically a linear transformation, right? So the linear transformation is essentially something that establishes a change in the frame. An affine transformation is a subset of the linear transformation. In particular, for 4D linear transformations, the affine transformations are those that have exactly 12 degrees of freedom. Because if you remember, the matrix had 4 elements that were fixed. So there were 3 zeros and a 1. So the affine transformations, more specifically, are those linear transformations that additionally preserve lines. So lines in the input get mapped to lines in the output, and they are not contracted to a point. So here I just want to give one quick example of the world and camera frames. So in the case of OpenGL or many such graphics APIs, the base frame that we work with is the world frame. So this is where this refers to the scene or the entire world. All the objects lie in this scene, so they share a common origin. This is how you model your objects. So this frame can later be converted into a frame that is with respect to the camera, because eventually you want to see everything centered at the camera or the viewer. So we do apply a transformation that allows us to go from the world frame to the camera frame. Like we saw before, this can be done via a simple transformation matrix. Initially, we assume in OpenGL that the world frame and the coordinate frame is exactly the same, right? So this transformation matrix M is exactly equal to the identity matrix I. So what does this mean? This means that your camera is actually located at origin. Let's do a quick thought experiment. Let's say that my objects are on both sides of the z equal to 0 plane, right? Now let's say the camera is located at 0, 0, 0, right? So we do want to see the objects that are behind the camera. So in order to do this, we should move the camera, right? So here is a scenario. So you have the camera here at the origin. So you notice here that the x coordinate, the x-axis, y and z-axis of the world and the camera, x sub c, y sub c, z sub c, are exactly the same, and their origins are also the same. So some of the objects are actually behind the camera. Now we want to make sure that they are also visible. In order to do that, I have to shift the camera, right? So this has to be incorporated by applying a transformation. Now, how does this affect the objects? It affects the objects by moving them away from the camera by a distance d along the z direction. And this can be written in the form of a matrix in this way. So we'll see this transformation in greater detail later. But this is, for example, one of the transformations that you have to apply to your objects in order to make sure that all of them appear in front of the camera, right? So we'll end the discussion with this thought experiment. We will talk in more detail about transformations in the next lecture.